The objective of this video is to understand how the transport layer security protocol works byte by byte. And to begin, I have a set of questions over here I'd like you to answer as we go through the lesson. Since this is the second part, we're going to focus on what the server is saying back while the client has already said hello. So if you go to this website to follow along, that'd be great, and I'll click annotations to make this small, and we're going to focus right here. These are all the bytes we're about to learn to see what's going on. If I click annotations, it'll make it bigger. But before I do that, let me just read this paragraph to briefly overview what we've talked about so far and where we're going. So it says here on a Network World article that the TLS handshake protocol allows the server and the client to authenticate each other and to negotiate an encryption algorithm and cryptographic key before data is exchanged. Now, in a typical scenario, only the server is authenticated and its identity is ensured while the client remains unauthenticated. And the mutual authentication of the server requires public key deployment to clients. So if you want the ability to basically write to a server, you're going to need to go through that key exchange as well. But seeing how it says in the typical scenario, only the server is authenticated, that's because many of the websites I go to, like this one, I'm not going to send the website any data to store. Because if I could send that website data to store, I could send a virus or something horrible, maybe instructions to delete the content of this, but since that's not possible, the server doesn't need to authenticate me, the client. Now, when a server and client communicate, TLS protocol ensures that no third party may eavesdrop. So this whole process I'm going through with you is so you can better understand cybersecurity, better understand this protocol. And byte by byte, because this process is followed, it's very difficult, near impossible, to tamper with any message and change that message in any way, thus the word forgery right there. So here we are under server hello. If you haven't seen the video of the client, go ahead and watch that one first. But when the server says hello back, the server is providing this information: the protocol version, the server data that's randomized, like the client had random data as well, again used in the handshake later on. It'll give a session ID, a selected cipher suite. So remember, the client sent what cipher suite it wanted to use. Now the server will be choosing which one. If there's compression, the server will select a compression method, and then of course a list of extensions. So let me scroll down here and read the first question. How large is the record payload? So in the record header, you have a byte for the type that is about to come. This is a handshake record. Then you have the protocol version of TLS, which in our case is 1.2. In the last video, I explained the complexity of using 3.3 as a version of SSL, which for us is TLS 1.2, but it's not too big a deal. You don't have to worry yourself too much with that. Just know that in this case, 3 and 3 will mean TLS 1.2. Remember, this is encoding. This is a person deciding numbers will mean certain things, even if the person is deciding that numbers will mean a different set of numbers. It's okay. And then the last 2 bytes in the record header is just the length of the record payload, which in our case is a pretty small one. It's 49 bytes, the answer to your first question right here. So the payload's 49 bytes. Let's go ahead and read the second 4 bytes coming through. These 4 bytes mean, well, the first byte means that a handshake message is about to occur. This is the server saying hello. So last time I said in class, with the client saying 1 means hello, the server says 2 to say hello. So if somebody gives you the number 1 finger in our class, you should respond with the number 2, and that means you're the server. So all data following this header is the payload for this message. So here's the first payload, here's the second payload, which is 45 bytes, which makes sense. Right here we went from 49 to 48, 47, 46, 45. So server version is up next. Let's read our next question. What does 2 mean in a handshake header? Oh, I already answered that, so that should be quick and easy for you to answer. Down here, how many more bytes do we have to go until the end of the handshake? 002D. I go over here, that was actually 002D. So it looks like I'm really asking questions about this handshake header. So in the header, it is saying hello back. And then it is saying you have 45 bytes left to go before I'm done talking. So to finish up the server's conversation, it'll tell us a server version number right here, which is 3 and 3. This long string of bytes is the server random data that we talked about before. The server provides 32 bytes of cryptographically secure random data. In this example, we've made the random data predictable to make it easier to recognize. And the TLS 1.2 spec says that the first 4 bytes should be the current time in seconds, but this is recommended against, so these might just be 0. I can't go into right now what it means to have fingerprints for hosts and servers, but that'll be later. Right now the session ID is 0. The cipher suite it has chosen is not these zeros, it's C013, which stood for this encryption method. The compression method is 0. Again, cryptographically secure things should not be compressible. Down here for our extensions length, it says the server has returned a list of extensions to the client because the server is forbidden from replying with an extension that the client did not send in its hello message. The server knows that the client will support all extensions listed. In this case, the client only wanted the server certificate to make sure to verify that the server it wanted to talk to, this one, right, is correct one. So the server has to prove that. And that's why this video is going by really quickly, right? We've wanted to focus on the server saying hello back. Well, I'm almost done already, and we're going to spend a little bit of time reading this part, the server certificate, which look how big that is. So let me wrap up this first part real quick, going all the way back down. The extension length is 5 bytes. Here's those 5 bytes right here. First, it's an assigned value for an extension, which is a renegotiation information piece. Now it says the ability to renegotiate a connection has been removed from the next version of this protocol, TLS 1.3, so this will no longer be necessary, so this is supposed to be going away. Over here, it's very redundant, right? Computers are redundant for good reason. It says 1 byte of extension data is about to follow, and here's that extension data. There's going to be nothing else. There's going to be no other extensions right now because in the first hello, the length of renegotiation data is 0 because this was the first connection. The way I like to think of it is the first big transfer. So if I go back up here, it specifically said, give me a signed certificate. Okay, so let's dive into this server certificate. You're going to see a lot of the things we've already seen. You have a header, you have a handshake header, you have a certificate length. Right now it's 808 bytes, and then again a certificate length. Now we're down to 805 bytes because the computer just told you another certificate length, so that's nice for a check. So going down here, we're about to read 805 bytes. This is everything that makes up a certificate. And if you're interested in the code, here it is. And when I click this, it'll take us to this page where I can click more annotations and get even more details about the certificate. So here we go with the certificate sequence. So right here, here's a serial number to the certificate. Here's the algorithm, SHA-256. So that's what these bytes mean. Now let's check on our questions real quick. It says, what are the 4 categories in the server certificate? Jump back over here, there's categories to a certificate. Oh yeah, so it says there's a type class, so universal, application, context specific, or private, and then there's 1 bit set if the record consists of smaller records, and then 5 more bits if type class is universal. Then type indicates either an integer, ASCII, string, object ID, etc. So that question is really focused on these categories or types. I want you to notice that if it's universal, then it's talking about some things we've already gone over in class. The concept of an integer, how ASCII works, basically what a string is. Strings must be made up of ASCII, right? Okay, so let's skip down to the algorithm because I always find that interesting. We're looking at algorithm SHA-256, like I said before. The question is, what is the algorithm? And now I need to tell you what the encryption name is. It says with RSA encryption. Okay, so let me wrap this lesson up. So you have your algorithm here, then you have an issuer sequence, a country, so we know what country the server is coming from, an organizational unit. So this looks pretty routine. It's going to be the name of the company issuing the CA, then validity. So it's like an expiration date right here. It's good from this time and date to this time and date. You have a subject sequence, another country. Why do you have another country? I don't know. Then you have a common name being sent, which is good because if I'm trying to go to this URL, I want to, at the end of the certificate, make sure the certificate is identifying the URL I want to go to. And since computers can only do a few things, this situation would be a comparison operator to compare the name in the client hello with the name of the common name in the certificate. As we go down, you'll see public key information, more extension information, then we'll have key usage. There's apparently two types, digital signature and key encipherment. I know I'm going really fast at this point because this is just deep information we won't necessarily need in this class.
And that's really it for this lesson. I know the picture says SSL, but remember SSL and TLS are very similar. What this picture is doing is abstracting away all the bytes that we were just looking at. You see here where we started, there's a client hello that is sent to the server. Then the server responds by saying hello back, picking a cipher to go with, and also identifying its certificate so we know it's the right server that we're looking for. And then more of the security stuff's going to happen, so the client's going to exchange a key, this key being useful to decrypt the message. So once that key exchange is done, the client will say finished, the server will say finished, and then they'll begin sending encrypted messages back and forth, each one using their own key to decrypt the message. And if you wanted to go deeper into this, you don't necessarily need to know what every single byte that is going back and forth is doing. You can look at it at a higher level of abstraction, like a screenshot of something in Wireshark. Still have plenty of numbers for you to evaluate. Remember, the whole point of a lesson like this is just so you know bit by bit what's actually going on, how the computer is interpreting this. Speeds that are really hard for humans to wrap their minds around. If you walk away with knowing the answer to these questions, I think you should feel pretty good about yourself.